Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, in today's lesson, we're going to do a little bit more with graphing, and I'm going to show you a strategy that you can use to help organize your work that you need to complete in order to fill in a table that eventually will be used to plot points on a graph that can be used for making predictions or estimations or solving problems. Before we get there, though, there are a few vocabulary terms I want to make sure that you get into your notes, into your journal. It starts off with dependent variable and then the independent variable. So remember, this chapter, we've been focusing on two variable equations. And our two variables are like the two variables in that situation that we had with John's redwoods. So remember, the y was equal to 4 times x plus 5 was the rule that we used to determine how tall the redwood tree would be after x number of years of planting, or since planting it. Actually, maybe we should say it that way. So in this situation, the x, the number of years after it was planted, affects the y, which is how tall the tree is. So in this situation, the dependent variable would be considered the y variable. And we tend to set up our tables and our graphs with this in mind. We always set up the rule so that y is equal to some expression that includes the x variable. So y, how tall is a tree? Well, it depends. What does it depend on? It depends on how many years after planting it you measure it. So we make the y the dependent variable because this is affected by the independent variable. And so if y is the dependent variable, then x has to be the independent variable, okay? And so independent is just the word that we choose for it. I like to think of it as the one that you have control over. Like, you can control when you measure the tree, but you can't control how tall the tree is. You have to control, am I going to measure it every 3 months, every year, every week, every 10 years? You exercise control over the independent variable, usually. Now, there are some situations where that doesn't really fit in. It doesn't make a whole lot of sense. A lot of times it does, and so I'll bring this up periodically when it makes sense to help you understand which of these variables should be your x and which one should be your y. And it's critically important that you eventually understand the significance of the differences between those two variables, because when you have a word problem, you have to determine what are we going to be exercising control over and which one is going to be affected by that. And so the one that you choose to assert control over will be your x variable, because that's the independent variable, okay? And then the last term, and if that's a little confusing now, it probably should be because it's being introduced to you. After we've worked with this for a few months, it'll start to be easier to identify and it'll make more sense. But anytime you learn something new, you've got to go through that uncomfortable moment in time where you have no idea what anyone is talking about. And through time and practice, it starts to make more sense. And that's how math is. I wish I could say everything was super easy, but if everything was easy and you knew it, you wouldn't be learning anything new. So you've got to be willing to accept that discomfort of not knowing something and trying to figure it out. That's where the real learning occurs. So just give it some time. And then we have a parabola. A parabola, most of the graphs that we've been working with are straight lines so far. But you saw an example of a parabola when we did that third lesson, I think, of the first chapter, when 4 of the graphs we did had straight lines, but one of them was U-shaped. Well, that's a parabola. A parabola is a U-shaped graph associated with quadratic functions. And what's a quadratic function, you may ask? Well, a quadratic function is a function where you've got y is equal to x squared. And so your independent variable at some point in this expression here is going to be squared. And it doesn't have to be just y equals x squared. It could be y equals x squared plus 3x plus 2. This particular, oops, stop it. Hey, y equals 3x, no, it's x squared plus 3x plus 2. Okay. Um, when you graph this, and this isn't gonna, you're not gonna be graphing this for quite a while, okay? You're gonna get a vertex, which is gonna be either the highest or the lowest point on the graph, depending on which direction it goes, and it's gonna have a shape of a U, okay? So there are lots of situations in science where you get graphs that are curved, okay? Whether they're curving up or curving down, depends on the nature of the situation. Like for instance, if you shoot a rocket and that rocket flies for a period of time before it comes back down to Earth, that can be modeled with this type of an equation, okay? We're gonna focus mostly on the linear equations, but periodically you'll see something like this pop up, okay? So let's move on. In lesson 3.1.3, you used a graphing tool to represent all of the XY pairs that follow a particular rule. Today you will learn how to make your graphs for rules and how to recognize patterns in the graphs. Now you could go to the online Desmos tool and you could use that. If you don't have graph paper, you don't have any means of doing the graphing, maybe you can go ahead and do that. Let me pause this for a second to make sure I don't have any answers shown here. Okay, so when you go to 3.1.4, if you want to use your Desmos graphing calculator to pull up and create a table and then plug these numbers into the table and then see them show up here, you can do that. But ideally, I mean, actually, if you want to do that, then practice with the settings to get, see what happens when you mess around with these things in here. Oh, feel free to do that. It's good to explore that. But generally, when we're in class doing this lesson, I like to have students pulling out graph paper and creating the graph themselves. I think it's a little bit easier, I think, to just set up a graph and on graph paper, on coordinate grid paper. You have control. It's right there in front of you. I mean, nothing really replaces paper pencil. If we do everything on the computer, then when you shut down the computer, you lose your graph. But if you do it on a piece of paper or in your journal, then you can keep it and you can reference it later when you're trying to figure something out. Okay, so I highly recommend doing this in a journal that already has graph paper or on separate graph paper. Okay, so this is called the class graph, but we're not in class right now. You're at home. So, you can just follow along with me and watch this first graph. I'm going to do a total of 4 graphs for this lesson, and you can watch me do the first one, and then please join me for the second, third, and fourth one. They'll be a little bit easier than this one. So what we do when we have a rule is we have to set up a table. Unlike setting up tables that look like this, I like the idea of setting up what I call an H chart. The H chart allows you to plug in all of the numbers, and you see how you got your variable right here. So if I said that x was going to be equal to -8, then y has to be equal to -5 times -8 plus 12. And so if you set this up in the middle, then you can simplify that. -5 times -8 is 40, and 40 plus 12 is 52. So one of our ordered pairs that would go on the graph for this particular rule would be where x is equal to -8, and y is equal to +52, and we would plot that point somewhere up here, okay? Now, this is a lot of different points for us to graph. So generally, what I recommend that you do is either graph points 0, 1, 2, 3, so you get at least 4 of them, or maybe -1, -2, -1, 0, 1, 2, and 3, So this is a good section. Where did we go? No, I said -2. -2, -1, 0, 1, 2, and 3. So let's just do those 5, okay? So I'll space it out a little bit. So if y is supposed to be equal to -5 times -2, what is -5 times -2? That's 10, correct? And then we add 12 to that, and our answer would be 22. And if y was equal to -5 times x, in this case, x is equal to -1, then that would be +5 plus 12 is equal to 17. And then the next one, we get a 0 there, so y is going to be equal. Can we just say that this is going to be 0? Because we know anything times 0 is 0, plus 12 gives me 12. And now I'm starting to get the hang of a pattern here. Y, what's 5 times 1? It's going to be 5 plus 12 is equal to 17. And then what do we have here? Oh, no, hold on for a second. Hold on for a second. See, this is where you start doing the problem mentally. And I already recognized I was making a mistake. I already have an output of 17 here. I shouldn't have 17 here. So what did I do wrong there? Maybe I should be showing my work. -5 times 1 is -5 plus 12 should have been 7. And then y is equal to -5 times 2, which is -10, plus 12 is equal to 2. So there are a couple different ways that we can plot these points. First of all, you want to make sure that your x and your y axis are scaled appropriately so that you can fit all the numbers that are in your table for your x values. The lowest that I have here is -8, but I'm not going to plot that point. So I decided maybe I would just go with -2 would be the lowest, and the highest would be 2. But if I wanted to accommodate all of these, I would have to have my x-axis go from -8 all the way to +8. And since my outputs, my y values went all the way up to 52, it's a good idea to go all the way up to 50 to 52, somewhere in here, and down to -52, because I imagine we're going to get into the negatives eventually here, right? In fact, the next one, if I decided to do it, would be -5 times 3, which is -15, plus 12 would be -3. And so you can see how we're going into the negatives there as well. Okay, so now for plotting, you can either plot these ordered pairs, or what I sometimes suggest students do is just code these ordered pairs with the letter of the alphabet. For instance, when x was equal to -2, y was equal to 22. And so rather than plotting that point there as -2, 22, we could just call it point G. And then point H would be at -1, 17, which should be right around here. And then I would be at 0, 12. So let's go to 0, 12, which would be right around here. And then J is going to be at 1, 7. So we'll go to 1, and then 7 would be right around there. You see how that looks like it's forming about a straight line? Let's get that in there a little bit. And then 2 was K, right? So it would be 2, 2. And then if we added 3, -3, that would be point L, would be 3, and -3 would be somewhere around here. Now notice how my x-axis, which I should probably label that, my x-axis is right here, and my y-axis is up here. And I'm not counting by the same counting sequence. I specifically counted by 1s on my x-axis because that's what I'm counting by here in my table for my x's. And if I wanted to get up into the 50s, I might have to count by 5s. Or I suppose I could have counted by 10s if I wanted to, but that would scrunch things together a little bit more. Now, let me go and find the extremes here. For this one right here, I already got the extreme up here, but what if x was equal to 8? That would be -5 times 8 plus 12. That's -40 plus 12 would be -28. Is that right? 40 minus 12 is 28, and you got more negatives and positives? Yes. So if I wanted to plot the extremes, I sometimes recommend that you do that. Let me go and plot point A would be somewhere around 52, and point Q would be at 8, negative 22. And if you plot those 2 points and connect those points, all the other points should fall in that row. Now, what have I done here? Have I made a little mistake? Have I made a bit of a mistake here? Where would my mistake be? 10, 20, 30, 40, 50. My counting sequences, I think, are correct, right? 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. 1, 2, 3, 4. Is this 8? 2, 4, 6, 8. Is that negative 5, 10, negative 15, negative 20, negative 22 should be around here. Oh, it's supposed to be 28. Look at that. Why did I say 22 instead of 28? It's negative 28. Now, see where the problem was? I recognize that there was a problem there because all of these points are supposed to fall on the same line. And when I connected my extremes, all these in the middle did not fall on that line. Why? Because I plotted my K or my Q in the wrong location. So let's get this guy down here to where negative 28 would be. That should be negative 28, somewhere around here, right? Negative 25, 26, 27, 28. So now let's see if things fall in line a little bit better. And they do, okay? So the more points that you can plot, the easier it is to tell if you've made a mistake with some of your plotting, okay? And if you plot the ones that are furthest away from each other, that makes it easier to get a straight line to make sure that all these others make it onto that straight line. Okay, so very, very critical that you make sure that you show some work in here and that you get these, they should be on a straight line, and that you plot at least 3 to 4 points and label them. It is extremely important. You want to make sure that your axes are properly scaled and they are properly labeled. My x-axis, my y-axis, and all my points are properly labeled as well. Whether you choose to label them with a letter of the alphabet or with an ordered pair. Let me go ahead and do 4 would be, what would that be? Negative 5 times negative 4 is 20. 20 plus 12 would be 32. So you could have done this. You could have gone negative 4 and plotted right here and called this negative 4, comma 32. It just, that takes up more space on your graphing, and so sometimes it's easier to just label here on your table and just use the letters of the alphabet for your labeling of your points. Okay, so I'm gonna suggest that you copy down each one of these rules, okay? And I'm gonna suggest that you create a different graph for every one of them because you might need to do different scaling, okay? So fill in the table of values based on this rule, and then choose what your greatest and your least x values are and what your greatest and least y values are, and make sure you can fit every one of those points on your graph. Then plot the points, and this should be a straight line, right? All of these graphs that we've been doing have been forming straight lines. Should form a straight line. So go ahead and graph this guy. You'll do the same for this guy. You might have to choose a different axis scale for your y-axis depending on what your output values are. And then the last one, this will be interesting. Maybe we'll check problems 34 and 35 first before coming on to problem 36, which is an example of a quadratic. So this one's going to have that parabola with a vertex. Okay, so go ahead and pause. Let's fill in these tables and then answer questions B, or question B, all those questions in B before you start graphing. Okay, unpause when you're ready to move on. I want you to do problems 34 and 35 before you unpause. So take your time with that. Alrighty, Let's see how you did. All right, so I did not set up the H chart. That's a recommendation for you, but I know a lot of students are able to solve these mentally. What I like to do is I like to start at 0. And so anything times 0 is always going to be equal to 0. So that means you got 0 here plus 1 means you're going to have positive 1. So one of our points on our graph is going to be 0, 1. And then I go and I do some of the positive, and then I look for a pattern there. See, there is going to be a pattern in your tables. If you set up your x-axis, or I'm sorry, your x values so that they're counting by ones like we have here, then you should know a pattern or see a pattern for your y values. A lot of times students make mistakes and they don't set things up in a table so it's not organized, and they just pick a bunch of random numbers for x and then try and plot those points, but then you never see the pattern. And we want this to be as easy as possible for you. So as soon as you see the pattern here, notice how this one is 3, and this one is 5, and this one is 7. You see how we're counting by 2s? Well, that pattern is going to continue. Remember the patterns with the tile, with those tile figures that we were looking at, where we were counting by 2s, and so when you go to the left, as you go down the figure numbers, they should decrease by 2. So all of these guys should follow the same pattern. Okay, so let's double check this. What is negative 4 times 2? It's negative 8, and negative 8 plus 1 is negative 7. Yes, that absolutely works. So now that we've got this table set up, now we can answer these questions. What are the greatest x and y values in the table? Well, the greatest value for x is 4, and the greatest value for y is 9. What is the smallest values for x and y? Well, the smallest values are negative 4 and negative 7. So there is a way that you can show this with what we call compound inequalities, where basically what I'm saying here is everything that's written here is the information written in these two sentences. Mathematicians like to create symbols to replace words because we want to write as little as possible to convey an understanding of the mathematics. So this is an inequality symbol that means less than or equal to. So negative 4 is less than or equal to x, which in turn is less than or equal to 4. So this is a way of saying this has the least value, and this is the greatest value. Same thing with the y. Y is somewhere in between. Its lowest value is negative 7. Its greatest value is positive 9. You can see that in the table right here. So now we move on to plotting these points. Now, if we've got our greatest value for x is 4 and our lowest value is negative 4, then I feel like I'm pretty comfortable counting by ones on my x-axis. Now, notice how I'm not putting a little tick mark in every single one of those spots here. I could do this and just count at 2, 4, 6, 8, 10, or if I wanted to space them out a little bit, I could have each one of those. Since I only need to go up to 4 for x, I could call this 1, this 2, this 3, and this 4. And I'll put in a 5 for good measure. But however we do our counting sequence, on the positive side of our x line, we have to do the same in the negative side. So this would be negative 1, negative 2, negative 3, negative 4, and negative 5. Now, if you have a different counting sequence, a different scale for your x-axis than I do, then that's going to affect how steep your line is. Both of them would be correct. This is one of the reasons why it's so important to label your graphs. Because if you properly labeled your graph, but you've labeled yours differently than mine with the scaling, then we could have two different looking graphs, but both of them would be correct. And all I would have to do is look at your work and say, oh yeah, you got it right. You just have different scaling. Same thing for the y's. Since I need to go up to 9, I am going to choose to count by ones for this one. So there's just 1, 2, 3, 4, 5, 6. But I'm not labeling every one. I'm labeling every other one. Okay? So now, time to plot these points. How many of these should I plot? Maybe I'll just plot them all. So 0, 1 is located here. 1, 3, 2, 5, 3, 7, and 4, 9. And I know you guys are looking at that and you're like, oh, Mr. Aaron's made a mistake. I'm like, yep, Mr. Aaron's made a mistake. I'll get to that in a second. -2, -3, -3, -5, and -4, negative. Oh, I didn't label these guys. Oh, you got to label the other part too. You can't just do the top part. So this was -2, -4, -6, -8, and -10. Okay, so -7 would be right around here. Okay, so if I connect these points, see how all of them fall on the line except for one? That's an indication that I've made a mistake and I know exactly which one was wrong. Where was my mistake here? This was supposed to be 1, 3, but I accidentally accounted over one line instead of one entire unit. This is the halfway point. Since that's one, that has to be 1/2, so that is in the wrong location. Now, how do I want to label these? I do not require you to label every single point that you graph. Label 3 of them. So maybe I'll label this one. This is 1, 3. I'll label this one. This is 3, 7. And maybe I'll label this one down here, which is -3, -5. Okay, so as long as you label 3 points and you've plotted 4 or 5 of them to make sure you got your straight line, then you've done your job. Okay, so one other thing to consider is it says plot and connect the points. Remember in our previous lesson when we talked about the difference between discrete and continuous graphs? Whenever you have a rule, you can technically make up any number you want for x, including all the fractional numbers. So anytime you're graphing a rule, you should connect the dots. It's not a discrete situation, it's a continuous situation, because x being an independent variable means you have control over it, and you can literally pick any number, including decimal numbers and fractional numbers. Okay, so we'll be connecting our dots for these graphs where we're given a rule. All right, let's see what we got for this one and see if we can identify a pattern. Here, I started once again with 0, 1, and then 1 became -2, since -3 times 1 is -3, plus 1 is -2. And then 2 became -5, 3 became -8. So it looks like as x increases by 1, y always goes down by 3. So if I go in the other direction, then it should increase by 3. So let me go ahead and check this one right here. -3 times -4 is equal to +12, and then 12 plus 1 gives us the 13. Okay, so we've got that right. Let's go ahead and graph these points. I'm thinking I need a different graph with different scaling, because I need to make it all the way up to +13. And so let's go ahead and I think I can do the same thing with my x-axis, but maybe I'll do my x-axis a different way this time. Maybe I'll just count by ones on this, and I'm going to label the 5th one. This is a trick of mine that I really like, and it's going to save you a lot of time. If you've got 1, 2, 3, 4, 5 units between 0 and 5, then you know each one of these is counting by 1, correct? So we don't necessarily have to label every single one of them. We could label this one as 10 if we wanted to, and this one as -10, but then we don't actually have to do that. So maybe I don't, since I won't be going out there anyway. And since my y has to make it all the way up to 13, maybe it would be better if I counted by 2s. So 1, 2, 3, 4, 5. This one would be 10. And 1, 2, 3, 4, 5. This one would be -10. Okay, so once again, you don't have to label every single one of these tick marks. As long as I can tell what your counting sequence is on your x and your y axis, and you've got them accurately labeled, then you're good. Okay, so now this time I'm going to choose to plot 4 of these points. Maybe I'll choose the 0, 1, which is here. Maybe I'll choose the 3, 3, -8, which is right here. Hold on for a second. I've got my marker too thick. I don't like it when it's that thick. Let me go there. So this is going to be 3, -8. This one was 0, 1. And maybe I'll choose -3, 10. -3, 10 would be located here. And let's connect those dots. I'll choose a blue line for this one. Does it form a straight line? Yes, it does. Oh, I said plotting 4, didn't I? Not just 3. I'm going to label 3, but I'm going to plot 4. And I'll make sure that -1, 4 falls on the line. That's right there. -1, 4. Okay, so properly labeled graph has 4 to 5 points. At least 3 of them have been labeled. Your axes are properly scaled and properly labeled. This is what we call a complete graph. Now let's go back for a second. There were a couple of questions there to answer. What does your graph look like? Describe the result. Well, looks straight, doesn't it? And when you read the graph from left to right, this one goes down. So as x increases, y decreases. So our graph looks like a straight line going from left to right. Now, how is this graph similar to the previous one? Well, this one was also straight, correct? But this one difference is that this one is going up when you read it from left to right. So as x increases, y also increases. So a couple similarities, a couple differences. They're both straight lines, and they actually both pass through 1, 1, or 0, 1, right? There was the 0, 1 here. You can see it in the table. Here's the 0, 1 in the table. There's the 0, 1. So they both shared that in common, was passing through 0, 1. And that point is actually called the y-intercept. We'll get to that later. The difference is one of them goes up when you read it from left to right, and the other one goes down when you read it from left to right. Okay, this one goes down. All right, so now go ahead, complete this table. We've got the same values for x, except for we included 1/2 and -1/2 in this table. So you want to be careful about looking for a pattern of growth here. This is a little bit different than the other 2 graphs. Go ahead and figure out all of those ordered pairs for each one of these independent variables. For each of these inputs, figure out the output, and then go ahead, label your graph, and plot those points, and label at least 3 of those points, okay? All right, so whenever you square a number, you multiply it times itself, correct? So that's what we're going to do here is for each one of these output variables, we're going to take the input variable and multiply it times itself. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16. 1/2 times 1/2 is 1/4. Now you go in the negative direction, and an interesting thing happens here. You end up getting the same output values over here as we had over here. It's almost like there's a mirror image or symmetry happening with those output values, because a negative times a negative gives you a positive answer, just like a positive times a positive gives you a positive answer. So now we take all these values, and I'm going to go ahead and I'm going to space out everything again like I did in that previous graph. So this will be 1, this will be 2, this will be 3, and this will be 4, because I want to be able to find my halfway point for x. So here you got your -1, your -2, your -3, and your -4, and I need to get up to 16. So I'm going to do the same thing here where this is 2, no, that'll be 4, 8, this will be 12, this will be 16, and this would be 20. And I feel like I shouldn't need to label these guys. but I'm going to anyway because we're not going to be graphing anything down here, right? None of our y values were even in the negative region. All right, so let's plot these points. Let's take 0, 0 is located here. Let's take 1/2, 1/4, which is going to be somewhere right around here. And then negative 1/2, 1/4 is going to be somewhere around here. We're going to take 1, 1, which is, if that's 2, this is 1, 1 right there. And this is negative 1, 1 right there. Then we have 2, 4 and negative 2, 4. We've got 3, 9 and negative 3, 9. And then we got 4, 16 and negative 4, 16. So you see how that's forming like a U shape here? And that would keep on going forever because we can continue adding on any values for x, and this is going to keep going straighter up and steeper up as, oh, that's terrible. Hold on for a second. I'm going to do a little trick here. All right, I used a little trick of technology, and it's not a perfect kind of a parabola. It's really hard for me on this particular program for me to get those lines perfect, but you get the general idea. We want these points to be on that line. Let me move this guy down a little further, this one down a little further. Move this guy over a little bit, but that's the general shape of the parabola, okay? Did I label my points? No. So this point right there was at 3, 9. This point down here is at 0, 0. And this point right there is at negative 4, 16. Okay. So what was the question that we had to answer here? Where is the vertex of the parabola that you graphed? Remember from our vocabulary at the beginning, the vertex is the point that is either the highest or the lowest point in your parabola. So the parabola comes down to 0, 0, which is its lowest point before it rebounds and starts going back up again. So our vertex for this particular parabola, for this graph, is at 0, 0. Okay? I am so sorry that this took a long time, but graphing is time consuming, and I felt the need to explain the process to you. But you really need to practice graphing as much as you possibly can. We will be getting into some lessons where we can use shortcuts for our graphing. It can be done very quickly. I'm going to tell you right now that I could graph this graph here in 30 seconds. From the moment I see the rule, I could create my axes, scale them, plot the points, and connect the dots in 30 seconds with the shortcuts that I know, and you'll get to that point as well. But right now, we got to make sure we're doing it right. And if you don't know the shortcuts, you can always set up a table of values, find those ordered pairs and plot them and label them, and your graph will be effective. Okay? All right, so head on over to the homework, and if they ask you to graph, please don't skip those steps. Please make sure that you do all the graphing that you can and that you make it as neat and orderly as you possibly can. So if someone else looks at your graph, they would be able to read it and understand it. Okay? All right, take care. Bye.
Hey, feeling good, like I should.